Thanks for coming. So delighted to have Gavin Crooks here today. He got his PhD in chemistry with David Chandler here in 1999 here in Berkeley. As a side project during his PhD, he saw this really interesting paper by Chris Dzerzhinsky, where Dzerzhinsky came up with Dzerzhinsky equality, it's referred to now, a relationship between an exponential average of a bunch of work measurements that have been observed through repeated doing the same protocol over and over again, some non-equilibrium process, and he found that was exactly equal to the exponential, the change in the free energy between the initial and final states. And this equality turned out to be a very important sort of watershed moment in a lot of things possible with non-equilibrium we're able to say things, not just things like the second law of thermodynamics inequality, but actually make exact statements about arbitrary far from equilibrium event phenomena. So then Gavin looked at this, a grad student, verified that there was a lot of skepticism about the result, verified that it was correct, and then came up with his own fundamental result that you can use to derive the Dzerzhinsky equality. He showed that the ratio of probability of a forward event divided by the probability of the reverse event was equal to the exponential of the entropy production for the forward event, and that is a fundamental relationship used to derive Dzerzhinsky, and you can use that to derive a particular form of second law of thermodynamics. So already in grad school had come up with a major fundamental result that is, in my mind, really, and that was back in, published that in '99, I think, or 2000. Became really important for non-equilibrium studies, which has affected certainly my group and other groups I know that work on this. So that's what he did for his, that was a side project during his graduate studies. Then he went on to become a software engineer for a year in 2000 at a startup. Then he did a computational biology postdoc here at Berkeley with Stephen Brunner, doing computational biology. Then LBL senior scientist from 2003 to 2017. And then went to Rigetti doing quantum computing for a while at a quantum computing company. Then Google X, 2019 to 2020. Actually did some consulting and a lecture here in chemistry in the spring of this year. And now he's at Normal Computing. Normal as in not quantum. So, and I think based on his he's going to tell us about it right now. So, anyway, thanks for coming.
Thank you. It was a pleasure to be here. It's always a pleasure to be back here at Berkeley. So as Mike was saying, I'm currently at a company called Normal Computing, which is, as we'll see, has multiple meanings, but one of which is not quantum. And this is a small startup I'll talk about a little bit towards the end. And one of the things we've been thinking about is how to do linear algebra using thermodynamic systems. So this is a paper from the archive, and we'll sort of talk about this paper. So, technical difficulties, man. What a second ago. You got it? So, I've learned a lesson here. There we go. Yeah. So the lesson is that, the startup world, everybody uses Google Slides these days because we're always doing talks online. And of course, Google Slides expects you to be online. And of course, there's no internet here. So, we're on my backup PDF. So anyway, this is the big picture. The general gist of what we want to think about goes under the rubric of thermodynamic computing. This was a phrase that was coined by Todd Conte like a few years ago. He's organized a little workshop to flesh out this idea, and it was like, "Do you want to come?" And I was like, "Yeah." And they said it's in Hawaii, so it was like, "Yeah, okay." But it actually turned out to be really cool. There's lots of interesting people there. And the general gist is, what do we mean by fundamental computing? What we want to mean by fundamental computing? There's sort of two aspects to it. And one is the idea that we should try to harness the physics more closely when we're trying to do computation. Right now, you try to do a computation on your computer with transistors. You're many layers abstracted away from the underlying physics. And if we can sort of get closer to the physics, maybe we can get closer, better energy efficiency and better speed, that kind of thing. And the other point is that as we bring energy scales down, thermodynamic effects become inevitable. At some point, we're inevitably going to have those. So again, our current generation of computers, they work very deterministically. Transistors are incredibly reliable. They switch on and off exactly when you want them to. But as we bring energy scales down, fluctuations start happening. And we can no longer expect everything to be deterministic. We've got to allow for errors. And we want to really think about noise then, ideally, not as necessarily a curse, but as a resource to be exploited. So where are we going here? So over the last 50 years, the energy that our computers use has dropped by many orders of magnitude. This is the energy to switch a transistor. And it's dropped like, what is this, like 15 orders of magnitude or something. And we're currently ballpark about 1,000 times KT, but 1,000 times thermodynamics. And KT, when we talk about thermodynamics, is sort of the relevant energy scale. And different fields have their own favored units of energy. So I just wrote some of them down here, whichever is your favorite unit of energy. That's KT at room temperature. And a computer might be running a little bit hotter than that, but it doesn't change these numbers particularly. So what's happened over the last 50 years is Moore's law. That over time, the size of our transistors has gotten smaller and smaller. That has led to sort of this corollary called Bernard scaling, that the amount of energy to switch the transistor has gotten less and less. The smaller the transistor, the less energy you need to switch it. What happened though is that we kind of ran out of Moore's law. Transistors are not really getting any much smaller. It used to be when silicon manufacturing conglomerates said to it like 20 nanometer scale or whatever it was, that was the scale of the smallest features on the chip. These days, those numbers are marginal. They don't no longer really correspond to the physical size of the chips, the features of the chip. And so as transistors stop getting any smaller, the energy per sort of transition in transistors has stopped getting any better. It's petered out. So about, estimates sort of vary, depending on the count, but something like 1,000 KT. This is still way above sort of fundamental thermodynamic limits, which is order of KT for a switch. If you don't do any extra special tricks like reversal computing. So in principle, you could do computing ground dissipation. So we're still a long way from where the thermodynamics really kicks in. Just always to point out that a lot of the energy also goes into the wires. Like the energy to move information across a chip is about 10 times that of just a transistor. We'd like to make the wires smaller, make the chips smaller. Unfortunately, you can't because, the chips are essentially too big. You try to make them any smaller, the power density would go up and it would balance. So it goes together. If we could make the computers more energy efficient, we could make them smaller. If we could make them smaller, they'd be more energy efficient. But we're in this regime right now where we're no longer seeing dramatic energy improvement. Like if you look at, say, NVIDIA's latest, massive GPUs, they've made those faster by cramming a huge amount of silicon into them. The actual energy per operation hasn't improved. They're just pumping more energy through them. So how do we get around this problem? Already, the amount of electricity that goes towards GPUs is also already a substantial fraction of the entire electricity budget. And we don't have an upper limit on the amount of compute we'd actually have to do. So how do we get, well, one is algorithms, just better algorithms. That's sort of a tide that raises all boats, hopefully. But maybe not. Sarah Hooker came up with this nice little paper a few years ago where she articulated this idea, which I think is, perhaps has been maybe said before, but maybe not as clearly, that our algorithms, our hardware really co-evolve. That the algorithms that we're using right now, take a look at the deep learning, they're really exploiting these GPUs. So that's partially because the GPUs already existed. So it's possible with a different evolutionary history of our hardware algorithms, we would have ended up in a different place. Maybe it's not the only way of doing these kind of problems. And so we should have an open mind to the possibility of different hardware architectures. Another big way around this problem is quantum computing. Quantum computing, we hope, will, for certain problems, be exponentially better than classical computing. There will be some problems with a quantum computer we just can't do on a classical computer. The problem is, well, there are several problems. One is quantum computers are just really hard. We're still many years away from actually having a practical quantum computer. And even if we did, it's unlikely you're going to get a quantum computer in your iPhone. They're going to be cloud devices. There's no current prospect of shrinking a quantum computer to something like iPhone. And even then, we don't actually expect the quantum computer to speed up all problems. We actually expect it to only speed up a small subset of problems. So most problems, particularly large data-intensive problems like machine learning kind of problems that we've got right now, are unlikely to benefit from quantum computing. Which leaves, a third possibility, which is some alternative novel hardware. And if you look out there in the world, there's actually many different approaches going on right now. Different approaches to trying to get around this problem. There's people working on reversible computing using memristas or spectronics or Ising machines. It's actually, you start poking around, and there's lots and lots of different approaches. So people talking about building NEMs, little oscillators out of silicon, and using those to do computation. And the reason is this is the right time to be thinking about these alternative approaches is, again, that ending of Moore's law. So what has happened historically, every time somebody's tried to build an alternative approach to computation or an alternative architecture, they've been steamrolled by Siemens. One of my favorite examples was back in the 80s. There was a serious effort to make superconducting computers, so classical logic using superconducting circuits. And one of the appeals of that approach was that, in principle, you could get very high clock rates out of that. Unfortunately, by the time they got it running, silicon had gotten so much better that they were left in the dust, and so the project got cancelled. However, and you can see this lots of times. I mean, people have often tried to build. There's been many historical efforts to build specialized hardware. We used to have Lisp machines or cellular automata machines, and most of these have, again, got just steamrolled by generic CMOS. One exception, I would think, is D. Shore Research has their Anton supercomputer, which is specifically designed to do molecular dynamics. And in terms of simulation time to Walcott time, nanosecond per second, it'll outbeat any generic GPU. But they've had to redesign it a few times to keep ahead of the generic silicon. Again, as we enter this regime of, it does look like we're getting substantial speed ups from CMOS for energy savings, with this new regime where there's the potential to, with these alternative approaches, to actually shine. The other side of this is let's say, noise. So So we're used to thinking about, again, a lot of our calculators have been very deterministic. And we want an exact answer out. But many algorithms, particularly again in this large data machine learning world we're in right now, actually use stochasticity. So this is sort of an illustration of the diffusion models that are behind things like DALI. So the basic idea is that we start off with some image, and then you imagine this forward process where we add noise to the image, and that destroys the image. We just have noise in it. And then, so what that becomes your training data. When you reverse this process, and then you're learning a neural network that will reconstruct the image going the other way. So this is an algorithm that actually tries to use noise in a useful way. So noise is not necessarily a bad thing. It's a resource that we can exploit with the right algorithm. So again, this is kind of like a generic thing we want to be thinking about is alternative computing approaches where we try to take advantage of physics and stochasticity. So in a regular computer, what's our sort of fundamental building block is like a bit. And sometimes people will talk about p-bits if we sort of go to the regime where things are now a bit stochastic. It was actually right back in the early days of digital computers. People worried about how to do digital calculations with errors. In the same way that we now worry about doing quantum computing, how do we add error corrected codes to quantum computers. That sort of research kind of fell by the wayside because the computers just got so reliable you didn't even worry about it. But we need to go back to that again as we start thinking about these more stochastic systems. Quantum mechanics, this may be a block sphere, you have a qubit, there's a whole set of possible states within this block sphere for bit. But if we're going to think about, really jumping to a stochastic system, the sort of unit of computation we want to think about is what we're going to call a stochastic unit, which is just some physical degree of freedom, which is going to fluctuate with time with some dynamics. And so as sort of the simplest, easily realizable version of this kind of stochastic unit, this is what we're looking at right now. It's a simple circuit with a stochastic voltage source and a resistor and a capacitor. And so this thing ends up just being a little harmonic oscillator. If you look at the voltage over time, it's basically bouncing up and down with some dynamics, which is going to be Brownian or Langevin, and some effective thermal noise. And that, therefore, that's the thing we're going to think of as our sort of minimum little units of computation. We could take a bunch of those, and we can connect them together. So these are meant to represent connections between these different cells. Each of these cells has its own capacitance. Each of these connections can have its own capacitance. So you connect the cells together with different capacitors. And what you get is a whole bunch of coupled harmonic oscillators. Like one of the simplest physical systems you can think about. But here it's tunable to the variance of each, the width of each well. So I want you to imagine like a nice animation here. So this is a little we have on our website. It's we're all physicists here, right? The harmonic oscillator should be second nature, but of course it's not for the rest of the world. So we have some nice little toys to play with. So there's a nice little thing here. You can just it's just two-dimensional harmonic oscillator, and you can twiddle the temperature and the covariances and watch these things about. I really enjoy that. It's amazing how anyway. Yeah. And so what's the dynamics then of such a simple system? Well, it's going to be, depending on how we actually set it up, it's going to just be basically Langevin. It's just going to be stochastic dynamics. If we add inductors, it's got a bit of momentum to it, so we undamped Langevin dynamics, or if we add inductors, it's just going to be Brownian dynamics. And again, that's really, in some sense, simple, but it's also, in some sense, kind of fundamental to how we want to think about computation at this very thermodynamic level. But we really want to think about continuous degrees of freedom, and they're going to have stochastic dynamics, and that stochastic dynamics is going to be larger bound to some good approximation. So what can we do with such a super simple system, computation? Well, the simplest thing we can do is we can sample from a multivariate Gaussian distribution. Right? So what we can put in is this A matrix that defines the capacitances. What we get out is a multivariate normal distribution, which is defined by the inverse of this A matrix, of the covariance matrix. So this A is the precision matrix. What we get out is a multivariate Gaussian with a covariance matrix. And we start at some point, and we let it evolve, we relax, just thermodynamic equilibrium, and we can sample it, and you are sampling from a multivariate Gaussian distribution. And the point here is that, although in some sense this is like the simplest possible non-trivial thermodynamic computing system, there's still actually non-trivial computational things you can do with this. So this is the sort of obvious first thing. You do sampling from Gaussian. That's actually potentially useful. What we've been poking at recently, though, is we can actually do matrix inversion. So again, this matrix goes in, this precision matrix, which is defined by the capacitances. So you give me a matrix, I can define the capacitive matrix. What you sample on the way out of this multivariate Gaussian is the inverse, the covariance matrix. So we code the system into basically this collection of harmonic springs. We let it equilibrate, then we measure the system for some time, and out of that we can actually extract out the covariance matrix. And so this is our first generation hardware. It's just a PCB, and these are, we've got 8x8 oscillators. So down the diagonal, these are the our degrees of freedom, and these are our coupling between them. We sort of have banks of capacitors that let us couple different degrees of freedom and control the capacitance. Again, I want you to imagine an amazing dynamic animated GIF right here, which is going to show that this is going to converge to the target inverse. We just put this up on the blog, so you can look at this. So this is just 4x4. This is sort of the inverse matrix going in. This is what the target output should look like. And after some number of samples, which you can see here, you get out some approximation, some reasonable approximation to the inverse. And this is just demonstrating the same thing. Again, this is actually animated. You can see the end result. So this and this are actually two different PCBs. So any of you who's ever actually tried to build like analog hardware knows that it is a difficult. That it doesn't necessarily want to do what you ask it to do. So we're getting reasonably similar results out of two iterations of the same hardware. And it's taken a little bit of a while to debug it. This is totally, again, this is just a PCB, so it's like this big. This is something that could be done on silicon, but right now we are sort of prototyping this on a larger scale. It's important to do that, even though this is an incredibly simple system at this point, because this keeps on this, right? What we're trying to do is think about thermodynamic algorithms that we can actually implement in the real world, and even right now, going straight to hardware and very simple systems forces us to think about this. Yes.
So you have a matrix of capacitors.
Yes.
And then what do you do to get the inverse matrix? So what do you measure in?
Oh, we're measuring the voltages on the between those different points. So on the back of the board, there's like an ABC curve on the back here. And so what you're measuring is these trajectories over time, and you're measuring out the covariance.
I don't think that tells me anything, so I don't get it.
Okay.
Now you measure voltages. The
Yeah.
voltages are basically noise, so they're AC. You're measuring some AC voltages.
Yeah.
And you need to create an entire new matrix because it's going to be the inverse matrix.
Yes.
So that means you have to do a great many measurements.
We do have to do measurements on this.
Okay, so which points, what do you measure at? You showed the circuit, it was a bunch of capacitors.
Yeah.
And so I have my 2 probes for my voltmeter, and what do I measure? What's my procedure? What do I see?
Yeah, fair enough. We are measuring the voltages on these these 8 points here. And then the covariance between those and the other points.
Maybe you should go ahead.
Sorry, can I ask you something?
Yeah, please.
So, is what you guys are using is the fact that the 2-point function of a Gaussian distributed random variable is the inverse of the matrix A? So if you compute it, if you measure the 2-point function of two of the
Yes,
oscillators,
right. So the cross correlation between different different variables gives us this covariance.
that is the right, and that okay.
So one question is, can we actually have any fundamental scale up? This is very much a work in progress in the sense that there's some subtle physical arguments on here that if we make some more broad assumptions about how the system works, then in principle this can scale quite reasonably. So a digital matrix scales like SD to the omega, where this is the matrix multiplication factor. We get a different scaling where, so we get the matrix in here. We also get out getting out these matrices that all depends on the condition number of matrices. So it's going to work for some matrices, it'll be really bad for others. And obviously how accurate you want it. Because if I don't want if I want an accurate matrix, I can do it quickly. If I want a very accurate number, I have to sample for a long time. But there's some basic assumptions on here. This will break down at some point as we try to scale this up. Try to scale this up to these kind of numbers, then you just physically run out of space. And there's other problems here that we have to worry about the amount of time it actually takes to load up the problem into the system in the first place. What else can we, so having got this, again, very simple system, we're kind of asking what other quantities can you actually calculate with such a physical system. Another one you can do is actually matrix determinants. So here I've written out the full, probability distribution of the multivariate Gaussian. So here are my covariance matrix. And you look at the normalization factor, we have the determinants of that covariance matrix. So the entropy of this multivariate Gaussian is the constants plus the logarithm of the determinant of the matrix. And so that means in principle we can use this to calculate the matrix determinants. I can start with this now becomes a non-equal process. I would start with a covariance matrix whose determinants I know, and then I would change that covariance matrix and change the distribution over time to some other Gaussian. And that would change the free energy of the system, and that free energy between some matrix system that I know and some matrix I don't would tell me the ratio of those determinants. Okay, who's taken StatMet recently? Grad students. Why is there no energy term here? Because the free energy has an energy term, but there's no energy term potential energy here. It wasn't in my previous talk. Hit something. Why is there no free energy? Why is there no energy change? What's the energy of a harmonic oscillator equilibrium? Oh, come on. Okay, go pick up David. David, what's the
Classically, it's 1/kT for each degree.
for each degree of K? So a harmonic oscillator at equilibrium is always a half kT average energy. And it's independent of how wide it is or how strongly coupled it is. So as you change this covariance matrix, the energy doesn't change, only the entropy change. So it actually makes this a little bit easier. So I just need to worry about this free energy change. And so in principle, I could measure this free energy change just as I would any other free energy change. If I could measure the work I'm putting into the system to change this potential over time, I could measure that free energy change. Either I could do this very slowly in a thermodynamic reversible way, in which case the work would equal the free energy change. Or in principle, I could do this fast and measure the work and do some sort of Jasinski average to get out that free energy change. So in principle, we could measure determinants of matrices with this procedure. This is not something we can do with our current hardware. You can't really measure in any reasonable way the work we're putting in. But I think this could be done, this experiment could be done, for example, with optical tweezers. We have a two-dimensional optical track. You could probably do this experiment. So work in progress is then to ask some interesting questions about the optimal control. This is, again, it's just a very simple multivariate Gaussian process. But we can still ask what the optimal protocol is. So I have my starting matrix of capacitances, my final matrix of capacitances, which I'm trying to change over some time. If I go infinitely slowly in a thermodynamic reversible limit, it wouldn't matter which process I took from one to the other. If we're trying to do this in a finite time, there is some protocol which will minimize that dissipation. And we can try to understand that protocol. So there's in particular, there's thermodynamic geometry, even a linear response sense, we can actually find what those optimal protocols are. And there's some more advanced recent work using Russian-span distances. So you can end up with this nice theory where the ensemble of possible states is connected on a manifold which has a Riemannian geometry, and then the optimal protocols in that Riemannian geometry are the minimum distances in the Riemannian geometry are in fact the optimal protocols, minimum dissipation at finite time. So this is very much a first crucial principle. This is what we want to do. Thermodynamic hardware. But we have to sort of tie this into actual practical applications. So the bigger picture is that we really want to think about thermodynamic AI algorithms, but ways of sort of implementing modern machine learning algorithms in hardware, trying to be as close to the physics as possible. Taking advantage of noise rather than treating it as a problem. So, there's many possibilities. Sort of Bayesian neural networks will feed into this. Probabilistic machine learning is a very natural fit for this kind of hardware. And again, these diffusion models feel like a very natural fit. And so, just wanted to talk a little bit about normal computing. This is the applied physics team. So we are a early seed stage startup. The main office is in New York, not far from Central Park. we're sort of the 20-person stage right now. For those PhD people and postdocs who may be looking for a job, we will be hiring in the near future. Your professors may not know this, but there are actually really interesting jobs out there in the real world outside of academia. This is our applied physics team, led by training leader Patrick Cole, who you may know from quantum computing work. A lot of the key ideas here are from Max Cipher. This is our blog with new results up presently on this particular paper. And we will be talking at Murex, several presentations. I will be at Crooks. Yeah, hopefully we'll see much more of this in the near future.
Time for questions.
Yes.
So the chip you made, from my understanding, sorry,
We go. So we like to do a chip, but going to chip is like another order of magnitude complexity. So we're prototyping a PCB.
sorry,
Yeah.
the PCB, the device,
We mistake we make all the time ourselves.
the device you
Yeah.
made uses 8 harmonic oscillators
That's it.
that are coupled.
Right.
Could you make the same device or a similar device with any generalized qubit? Like suppose you have a probabilistic bit. Can you make the same device that does the same thing out of that?
Yes, I mean obviously it depends on the particular physics, but again, coupled harmonic oscillator is a very fundamental generic thing which you can build out of many different out of many different hardware. So we're not like wedded to this particular implementation, right? It's just something that's very convenient to build.
But if you had, like, say, just to pick one, like a magnetic probabilistic bit.
In potential, yeah. There was, I mean, there's other considerations, like further down the line, you would like to make sure that the hardware you're using can be built on silicon, right, on a chip. Because, anything you do, at some point, it's got to compete with CMOS, and you've got to, there's 50 odd years of expertise there. So, the thing, there were people have come up with more exotic ideas in the past, but anything that can't be put implemented in silicon is probably not so. Yes.
So, it is not clear to me how this approach is better than what we already have. I mean, it seems to me, for example, how does this approach compare to running Monte Carlo simulations of these 3 field models that you guys are building, like on real hardware?
Right. So obviously this hardware, we try to figure out what its energy cost. It's going to be quite hard. The idea, though, is that ultimately we can bring this way down and implement it with very low level. So if I do a digital simulation, right, there's many levels. I'm doing floating point at some point. I'm doing many floating point operations. Those transistors have been driven very hard on and off, so that with a very strong clock. Even the clock is problematic. Right? When you start looking at the thermodynamics of a precise clock, that has a thermodynamic cost to it. So again, it's all about trying to get away from that determinism that's inherent in the way we currently do our simulations, and try to go to something that's much more so the idea is that we're closer to the physics, and with less layers in between. Now, clearly we haven't shown that is
So, for example, is there any sort of estimate that you can do on how flexible the hardware could get to be? How many different matrices A can I consider by considering like how easy will it be to change whatever couplings I need to put in between my different LC resonators to describe different matrices A? Is there an estimate, a physical estimate that one can do?
in what sense? So, right now we have banks of capacitors between these. So we can, have different capacitors. So we select some, discrete set of capacitors between each. That needs to be improved too. So that's kind of, there's a finite number of making it relevant. We have, a lot of this, particularly this early stage, is about understanding how to add error robustness to these systems. If we're doing, people understand how to build digital hardware, and it will do what you want it to do. If you get in the analog regime, it's much harder to get the hardware to do what you design it to do. So we need to design in error robustness. And that's one we thought about, and we will hopefully talk about it. Just that getting out of different matrices with a limited range of assets.
Is there a possibility of condensing your, making it small, say like each oscillator would be, say, a unit crystal? That
Would be
one unit of crystal.
potentially, yeah.
How far down could you go?
Well, okay, so this particular implementation, you put it onto silicon. Capacitors actually end up being quite big and inductors being really big. So, there's problems with that. So we're looking for there's alternative approaches to implementing the same basic idea.
What about the harmonic oscillator?
You can, but then it's a question of, we need something practical though, right? So certainly, yeah, a small system is possible. It's a question of finding the right substrate where it's still like manufacturable and measurable and all these other things, but also nice, the smallest.
Have you ever thought about how far down you can go? Practical ideas?
Yeah, not that we're talking about. Right?
Yeah.
Certainly, it's in the things that we are actively working on.
One of the things that pops up in all these analog computing is connectivity. Is there any chance of using these principles or scaling to large systems?
So, scaling this directly to large systems would be, again, the connectivity is one of the things that was probably killing us. Try to make this large system. There just won't be enough room for the wires. And so, yes, that's a problem. We're going to have to find one.
Or in the sense, is there principles that from thermodynamics or something that we can use to say couple large number of systems, some collective state?
I would like to think so, but you've got to crystallize these.
So, I'm wondering, this reminds me a lot when condensed matter physics we're talking about something observable at finite temperature and you have, say, harmonic phonons. You generate a bunch of configurations and you sample your observable at that given temperature. And then from the mean value theorem of integrals, in principle there is always one configuration that will give you the exact unsampled average. And there are approaches that try to find that configuration, give you a narrow distribution around it as much as possible. So I'm wondering, do you think that such approaches could be applicable to what you're doing here? Do you think it's relevant at all?
No, we thought about, it sounds like sort of that same kind of idea. For those particular systems, for example, I mean, if you just wanted to, in some cases you might just want the bottom of the well. And so it's a harmonic system, so the mean is the same as the bottom. So you just cool it basically in front of the bottom. So, there's some possibilities of particular sort of more machine learning algorithms that will fit into the same paradigm where that's actually the right thing to do rather than sampling is just finding the. So yes, again, in some cases that doesn't work. Yeah.
I was wondering if you could give us a glimpse into the crystal ball a little bit, and so what does this novel, what would thermodynamics computing kind of unlock?
Well, I mean, the dream is that we get this new regime of computing devices whose fundamental energy scales are approaching the thermodynamic energy scale. So tens of kT at most per operation. So way, way less energy than current hardware. And there's arguments that's feasible. One example is, my brain runs off about 20 watts, and some estimates. Estimates vary. Like a synapse runs at something like millions of kT per firing, and it's not quite clear how much computation we should compare that to. But if you compare it to, say, a floating point operation, that's maybe a tenth of the energy of a floating point operation in a current generation GPU. So there's definite possibilities of dramatically reducing the energy costs of computation. And that potentially opens up, again, you look at these AI algorithms, partially they're data limited, just how much data I can stuff into them. But partially they're energy limited, just how much energy it takes to run ChatGPT is non-trivial. And so what we are looking for, one way or another, is to massively reduce that energy budget. That would just open up a whole range of possibilities for implementation. Yes, please.
I may have missed this, but by going to thermodynamic energy, we're using the deterministic nature of our computing.
Yes.
So is that a favorable exchange? Are we gaining more energy than we're losing information?
That's a good way of looking at it, actually. One way, though, is that as we reduce the energy range, being random is inevitable. We've got no choice in that. The computers will just stop being deterministic. So we have to do some sort of error correction. We might as well try to take advantage of it. And so, yeah, the idea is that in principle, even though it's stochastic and getting errors, and you reduce the energy, you don't necessarily lose the information. You can still do computation. In principle, you can do computation with zero energy costs, reversibly. It might take infinitely long. Try to do it from reversibly, you're going very slow. So there's still, these interesting trade-offs with time and energy.
So I think I kind of get the argument that, like, if we're going to reduce the energy side, then we're going to reach the thermodynamic limit, but here we're using the thermodynamic properties of the system. But you're always going to have to observe the output of your circuit with something that can reliably measure voltages.
Yeah.
So what do we do with that?
This is an excellent question. So as you said, right now, right, we have this, this thermodynamic system, but there's on the back of that board, there's a USB port, and there's to make this practical, you have to start being able to couple. This has to be the subsystem. You have to couple these subsystems together into some larger conglomerate, and then at the edges of that, the digital goes in, and digital goes out. Now, how we do that is to be determined. But yeah, obviously, that is, what we're looking for right now is sort of units that then can be connected together with more elaborate and more complicated algorithms. But yeah, I think at some level, you're still going to want to, some part of your computer still wants to be, perfectly reliable to keep an eye on the bits that aren't.
One more burning question, if there's one. Thanks very much.
Thank you.